Hi everyone, this will be a short series on graph theory. Um, I decided to do a little series on graph theory because it is something that I really enjoy, and it happens to be very applicable to computer science, which a lot of my students are computer science students, so it meshes well with my interest and their interests. And I think that graph theory is not something that a lot of at least undergraduate students study, even though it is very accessible to a lot of students of different levels. The most you need graph theory is to start at least is a pre-calculus knowledge of the subject. As you get more advanced into math, into graph theory, and in math, you'll see its applications into more advanced topics. But in and of itself, you really do not need too much outside information. So I think that is very appealing to graph theory, and it's rather intuitive. Um, the first Euler was the mathematician who developed graph theory, and the first book that was written was called Dots and Lines. That's really what a graph is. It's just dots and lines between them. So it's very intuitive. A lot of the theorems we'll see are make a lot of sense. They're believable because really you can see everything that's going on in graph theory, which I do like. I think I'm a very visual person. I really need to see things to understand them. So that's why I like graph theory so much. So to begin, we're just going to develop some definitions and might go into some theorems, but nothing too complicated. But this first lesson will be very definitional, just so we can have the same language and so you know what I'm talking about. So let's begin. So, what is a graph? So a graph is defined by two sets. So we usually denote the graph by G, and the two sets it's defined by will be a pair of V and E. So V will be our vertex set, and E we call the edge set. So what are vertices and edges? So a vertex is just represented by points in your space. And then edges are represented by lines between vertices. Forgive my handwriting, and this is very new to drawing on a computer, so bear with me. So Vi and Vj are vertices. Sometimes we'll say that Vi is connected to Vj by an edge. So this means connected. So Vi, Vj, the pair, that's how we'll denote edges, is in the edge set if Vi is connected to Vj. So when you talk about elements in your edge set, we can have some definitions of graphs based on what our edge set looks like. So, for example, if the edge set has ordered elements and what I mean by ordered elements, I mean Vi, Vj is different than Vj, Vi. So if you have edge sets that if you have edges where the ordering does matter, where what is in this first position matters and what is in the second position matters, then we'll call the graph directed. So what this means, let's look at two edges, different edges. So here's Vi and here's Vj. So Vi, Vj this way is different than Vj, Vi this way. So generally we'll draw arrows to determine direction. So this edge is coming from Vi and pointing towards Vj, so we draw an arrow this way. And then Vj over here to Vi will denote by an arrow this way. So this is Vj and then Vi. So generally for this series, we'll be considering non-directed graphs. So it doesn't matter how I order the vertices in an edge, and we generally won't be drawing arrows. But for some things, we might bring it up. So another property you can talk about is of a graph is if a graph is called simple or not. The graph is called simple if there are no repeating elements in the edge set E, nor are there any elements of the form Vi, Vi. So this is what we call a loop. So here is Vi, Vi. So it's a edge where it starts and ends at the same point. And then a multiple edge is a repeating element. So this would be Vi, Vj. Another Vi, Vj. This is different than a directed graph. So just a note, directed graphs like this is still simple, right? Because Vi, Vj is different, right, than Vj, Vi. So it's not a repeating element. This would not be simple, though, if you had two edges pointing in the same direction. This is not simple. So just be aware of that when you see arrows in your graph. Don't always assume it's not simple, right? All simple means is no repeating elements and no loops. So if you know your graph is directed, and you have Vi, Vj, and then also Vj, Vi, well, those are different elements because that's in a directed graph. Okay, so you can define graphs based on, uniquely define them by their vertex and edge set. So let's just draw a couple graphs and see what they look like. So let's say our vertex set, we have, let's say 4 vertices, v1, v2, v3, and v4. And then our edge set, remember our edge set are pairs of vertices. So I cannot write any pairs of vertices that are not in the vertex set, right? So I need to, all of my edges need to be of elements in the vertex set. So let's say I have the edge v1, v2, edge v2, v3, v1, v4, and v3, v1. So how could we draw this? So let's just draw the 4 points to begin with, the 4 vertices. This is v1, v2, v3, v4. Let's draw the edges. So v1, v2, so there's an edge between v1 and v2. There's an edge between v2 and v3, between v1 and v4, and between v1 and v3. So this is what the graph looks like. So, by the way, unless I say otherwise, everything will be assumed to be non-directed graphs. So so if you see a graph, assume it's not directed. Directed graphs are a bit more interesting, so you might be told if a graph is directed. Okay, so let's do a different graph. Let's do vertex set A, B, C, D. They don't always need to be V's. And let's have the edge set as BC, AD, CA, and AB. Let's see what this looks like. So it doesn't matter how you arrange the vertices. So I'll do it this way for this graph, A, B, C, D. Let's draw an edge between B and C, edge between A and D, between C and A, and between A and B. So that's this graph. So what's interesting about these two graphs that we just did was that, in fact, they are the same graph. Not quite the same, obviously. They look different. But there's a way in which they are the same. So this is this graph. So what we can do, let's rearrange some of the vertices and see what happens. So first, I'm going to move D over to the side here, and I'm going to move C over to the side. So I have A, D, A is connected to D still, A is connected to B, C is over here, these two are connected. And now I'm going to move D, I'm going to wrap it around. So A, B, C, and D is wrapped around the other side. So now look at these two graphs, they're essentially the same. All I've done was rearrange some of the vertices. So now notice I didn't remove an edge, I didn't add an edge. I didn't move an edge to another vertex. All the edges are the same. If I were to draw the graph this way, in this arrangement, I would still get this graph. So these two graphs are the same. But one little tidbit is that, or difference is that, well, these still are different graphs, right? uh, um, this graph has vertices A, B, C, D, but this graph has vertices V1, V2, V3, V4. So they really are different vertices. However, if I relabel V1 and just relabel that as A, relabel V2 with B, V3 relabel to C, and V4 relabel to D, then they will be the same graph. So there's a name for that, this relabeling and reordering. So what is that name? So two graphs are called isomorphic if they are equivalent. Up to relabeling or reordering. Or rearrangement. So what does that mean? So let's take our two graphs. So they are different graphs because they look different. But if I rearrange them without really changing the structure of the graph, then they'll look the same. So why the word isomorphic? Well, iso is a Greek root for same or equal. And the morphism part is this action of changing one to the other by this relabeling or rearrangement. So it's a type of morphism, a type of morphing of the graph where it's equal. It does not change much. So this is called an isomorphism of graphs, where you're just rearranging things and not really changing the basic structure of the graph. So this is actually a very interesting and concept, which seems very intuitive, but this has a lot of this is actually an open problem. So I'll say what the open problem is. A lot of open problems in graph theory that seem very intuitive. So, and this is very interesting it's interesting to believe that this is true, or this is not known yet. There is no known algorithm. Oops, sorry. There is no known algorithm to determine if two graphs are isomorphic or not. Well, I should really say two graphs are isomorphic. There are a lot of properties where you can tell if two graphs are not isomorphic. Very easy ones, if their vertex sets are different, different amount, and their edge sets are different amount, well, obviously they can't be the same graph if they don't have the same number of vertices or edges. So let's talk about some other ways we can determine if two graphs are not isomorphic. So that's kind of the problem with this question, is that there are a lot of ways you can determine if something if two graphs are not isomorphic, right? But that does not exhaust all the possibilities, right, to make a graph isomorphic. That's a a very stronger statement to determine if something is true. It's not enough to show all the ways that it could be false, right? Because that could be endless. But the goal is there an algorithm to show that two graphs are isomorphic? So it's still an open problem, and if you figure it out, you probably get a Fields Medal. That's a interesting problem there, and again, there's a lot of ways you can begin to determine if two things are not isomorphic. So here's a definition to get us started. So essentially what we're going to be doing is looking at properties of the vertex set. So the degree of a vertex is defined by the number of edges. From that vertex. So let's just do an example that we had before. So this is V1, V2, V3, and V4. So generally when you list degrees of a graph, we do it from the smallest degree up. So look at V4 here. There's only one edge emanating from V4, so that has degree 1. V2, what I like to do is draw little circles around the vertices and see where they intersect. V2 has 2 edges. V3 has also 2 edges. And V1 has 3 edges. So this is called a degree sequence. So you just list the degrees of the vertices from smallest degree up. So why is this helpful? Well, let's look at a graph where the degrees are different. So let's draw our first graph that we had. And then draw another graph. And we'll be able to tell why this graph is not isomorphic. So these things are not equal. Generally, we do a little squiggle above the equal sign to determine isomorphic. So why aren't these graphs isomorphic? Well, very easily you can see that this graph has no vertex of degree 1. Right, this one is very easy. This graph, you can easily see there's a vertex of degree 1. Right, but this graph has no vertices of degree 1. In fact, all of them are of degree 2. So, and also then you can also see it has no vertex of degree 3. So immediately we can tell by the degree of the vertices. So all are of degree 2. We can see by the vertices that these two graphs are not isomorphic. So by the way, we might talk about this later, but a graph is called regular, or really deregular, if all vertices are of degree 2. Or sorry, degree D. So this one is 2 regular. Another word you might hear for degree is valence. You might use that interchangeably with degree. So the valence of a vertex is how many edges are coming from it. So based on this definition, and based on what we were saying before, that there's no known algorithm to determine if two graphs are isomorphic, you should be able to tell that the converse isn't true, right? If you have two graphs with the same degree sequence, it's not guaranteed that the two graphs are isomorphic. It's a necessary but not sufficient condition. That's what one might say. So all graphs need to have, all isomorphic graphs need to have the same degree sequence, but not all graphs of the same degree sequence are isomorphic. And let's do some examples. Examples of non-isomorphic graphs. With the same degree sequence. So the first one, I'll do an obvious one. So our original graph, that degree sequence was 1, 2, 2, 3. And this one is obviously not isomorphic, and hopefully you'll see why. So this one is 1, 2, 2. This one is actually 3. So here, loops count twice. Right, because you do this little circle trick, right? Draw a small enough circle, and it's going to intersect the circle 3 times. So that's a way you can count degrees and not get confused with loops, right? Loop is a single edge, but since it starts and ends at the same point, the graphs will be, or the degree is 3 for this case. Well, rather, the loop counts twice for the degree. But these are, okay, so they have the same degree sequence, but these are obviously not isomorphic, right? For starters, our first graph is simple. Right, and our second graph is a multigraph. Right, I'm not sure if I define that, but multigraph is not a simple graph, right? Because it has a loop. But these have the same degree sequence. So that was kind of obvious one why they're not isomorphic. But let me give you an interesting one where you have 2 simple graphs, but it turns out they're also not isomorphic. Okay, so here's one graph. And here's another graph. So you'll probably be able to see why these graphs are not isomorphic pretty intuitively. But this leads itself to another definition to really explain why they're not isomorphic. So looking at these 2 graphs, right, they look pretty similar. But the biggest difference is that right, the square here, they kind of swap places, right? Not only did it swap places, but this edge didn't swap, right? Maybe if this edge was over here instead, then it's possibly or there or maybe there, right? Then maybe the 2 graphs will be isomorphic, right? So maybe you can see immediately why they wouldn't be isomorphic. But we can kind of explain why the definition. So first of all, let's just count the degrees. So this one is degree 1. This one is degree 3, 2. This one is 4, 3, 4. So degree 2, degree 3, and degree 3. So this is 1, 2, 2, 3, 3, 3, 4. Now let's count this one. So this is 1, this is 3, this is 3, this is 3, 2, 2, and this is 4. So it has the same degree sequence. 1, 2, 2, 3, 3, 3, 4. So here's a way you can determine it, or a neat way to, kind of a sieve method to determine if something is not isomorphic. So let's take, there's only, for each graph, there's only one vertex of degree 1 and only one vertex of degree 4. So in our relabeling, these would need to be the same vertex, right? Let's suppose they were isomorphic, right? Then these would need to be labeled as the same vertex. However, maybe you can see pretty easily that 1 and 4 in this graph, 1 and 4 are further apart. So I haven't really defined what that means than in this graph, right? 1 and 4, we can draw a line, right? There's two edges connecting 1 and 4, right? Go through this vertex from 1, connect this edge here, and then this edge here. So there's two edges between 1 and 4. However, in this one, once I hit this vertex, I have to go either up or down, but none of those ways would bring me to 4. Right? So the shortest distance between 1 and 4 in our first graph is 3. But this one, the shortest connection between the two vertices is 2. So that can tell you immediately if these are not isomorphic, right? Because, right, again, we cannot add edges or remove edges or move relations between vertices around. So if suddenly the vertex is further apart from another vertex in my relabeling, then clearly something went wrong and these are not isomorphic. So that leads itself to a definition. What does this mean? Further apart in what way? So we're going to define a definition. We're going to make a definition. It'll kind of lead itself into why these are not isomorphic. Okay, so a path, this is a definition. A path is a sequence of adjacent edges. So, for example, let's do our original graph. V1, V2, V3, V4. This would be a path. V4, V1, and then what's an edge adjacent to V1, V4? V1, V2 is adjacent. What's an edge adjacent to V1, V2, V2, V3, and then so for V2, V3, I cannot choose V1, V4, right? Because it's not adjacent. So adjacent means that they share a common vertex. Two edges that share a common vertex. So I could do V3, V1. So this is a sequence of edges, and this is adjacent edges, and this is called a path. So just very intuitively, what that means is that I go from V4 to V1, from V1 to V2, and then V2 to V3, and then V3 to V1. Another way to define a path is by its vertices. So you start with vertex 4, Then you go to vertex 1, vertex 2, vertex 3, back to vertex 1. So either way, this would tell you the path. However, just be careful with this one. This definition of a path would probably not be good for multigraphs. Right, and if you have a multigraph, you might have multiple edges, and then you would have to care about which way you get from V2 to V3, for example. There could be two V2, V3s, and if you define the path by the edge sequence, that might be a bit easier to do. So then it's very easy to see, right? If I have two isomorphic graphs, upon this relabeling, the shortest paths between points should be preserved because they are the same graph. So what was such a problem with the graph that we had before? Well, the easiest way to tell it was not isomorphic is because, remember, there was only one vertex of degree 1 and only one vertex of degree 4 between the two graphs. So we know those had to be the same under the supposed isomorphism. However, the path lengths were not preserved. All right, so let's give some names here: V1, V2, V3, V4, V5, V6, V7. Right, the path length between V5 and V2, you could have V5, V4, V3, V2, and let's say A, B, C, D, E, F, G. This path length from E to F is just E, D, F. So this path was length 3. And this path was length 2. So actually, while we're here, one thing to watch out for your path sequence. I generally like to do, if I'm not working with a multigraph, it's just visually, I think it's easier to see and less things to write if your sequence is of vertices, adjacent vertices. But a drawback of it, of course, is that you just have to subtract one off, right, from the number of vertices, right, number of edges. So in this first degree sequence here, right, there are 4 vertices, but it's really 3 edges between them. So anyway, so in short, we can easily see that these two graphs are not isomorphic because even though they have the same degree sequence, they do not preserve path length. Okay, so just to get through a couple more definitions. So we may, more definitions. Let's start with a cycle. A cycle or a circuit is a path that starts and ends at the same vertex. So here's a way that the vertex sequence is a bit more preferable. Let's just give our nice graph in the beginning: V1, V2, V3, V4. Here's an example of a cycle. v1, v2, v3, v1. That's a cycle. Here's another cycle of v4, v1, v2, v3, v1. That's a cycle. So all the path starts and ends at the same place. So this is the second one, v4 to v1, v1 to v2, v2 to v3, v3 to v1. And I forgot to end this cycle. And then v1 back to v4. It's okay to repeat an edge. That's because a path it's okay to do that. We'll talk about when it's not okay to do that, but for a cycle, it's okay to repeat an edge. That's all a cycle is. So to finish off the definitions, we'll talk about an Eulerian path. So an Eulerian path is a special type of path. It's a path that passes through every edge only once. So why is it called an Eulerian edge? Or, sorry, an Eulerian path? Well, it comes from the word, the name Euler. Euler pretty much founded graph theory. And the first big question that Euler had, which really developed graph theory, was the bridges of Königsberg. I'm probably spelling and saying this wrong, but Königsberg, something like that, which is it's a town in Germany. And there were these, there's a river that passed through the town. And there was bridges between the in the town, between the land masses. So, my not great representation or drawing of the problem, but it's the general idea. So there were these 7 bridges, and Euler was walking through town one day and asked if it was possible to walk through all the bridges only once. So, for example, the path I drew here, I would not be able to go across both these bridges without having to cross one of the bridges again. So maybe I just started and did my path wrong. So this is what Euler was thinking about. Is there a way to cross all these bridges and cross them all, but only cross each bridge once? So this really developed the graph theory. So what he did was, thought, well, it doesn't really matter where these, lands are, so really you can contract everything to a point. And the size of the bridges didn't matter, so all the bridges can be just lines, essentially, right? It doesn't matter how big they are. So this really developed what graph theory was. So the lands became vertices, the bridges were edges, and this developed the graph. This is kind of the first graph in existence. So just to draw this a bit nicer, this is a nice thing about the graphs, is that really simplify the drawing. So now looking at this graph, is there a path that goes through every edge at least, goes through every edge only once? And the answer is impossible. So we'll talk about this next time. We don't really have enough time now to get into it. But this is the general, this is really what founded graph theory. And I'll leave it to you until you watch the next video to really think about why should this be impossible. And once you see the answer, it's kind of clear why it is impossible. And so it's an intuitive kind of answer. So I would think about it before looking at the proof to kind of give yourself a reason why it is impossible. But however, we'll be able to prove pretty easily if something is not an Eulerian, what's called Eulerian cycle. So let's do that. An Eulerian cycle. Sorry. Oops. Still not used to this. Okay, an Eulerian cycle is what, just based on the previous definition, is a cycle that passes through every edge once. So our original graph, we can tell pretty easily through one observation why it's impossible to have an Eulerian cycle. So think about that for a little bit. Maybe pause the video and try to think about it for yourself. But the answer lies in this vertex here. So if a graph has a vertex of degree 1, then no Eulerian cycle exists. So let's think about why that's impossible. So there's two possibilities, right? Either you start at the degree 1 or you don't. So let's suppose you don't. Suppose you don't start. So here's your degree 1. And maybe here's some other, you don't know what the graph looks like. It could be this very interesting graph. You don't know what it looks like. But suppose there's at least one vertex of degree 1. Let's call it here. So it's very intuitively, at some point, if there's an Eulerian cycle, at some point you're going to hit this vertex here, and then you're going to cross over to this vertex, to this edge. But immediately you can see why there cannot be an Eulerian cycle, because for it to be a cycle, you would need to end at your starting point, right? But once you have a degree 1 and you cross this over this edge, you can't come backward, right? Because that's the only edge connecting that vertex, and you can't cross that edge again, right? This is not a directed graph or multigraph. So there's no other edge connecting that to that vertex. So immediately that's impossible. So next case, and this is very easy to see why this is impossible too. So suppose you do start at the degree 1. So if you start at the degree 1, well, immediately there cannot be a cycle, right? Because once you cross this edge, right, there's no going back, right? So you cannot reach back to your vertex. So if you ever have a degree 1 vertex in a graph, then that means no Eulerian cycle exists, right? Because you cannot come back to your original vertex. So if a graph has a degree 1 vertex, then no Eulerian cycle exists. So we'll stop there for now. I think it's a very clear, intuitive way why that doesn't exist. If you have a degree 1 vertex, really you can't come back to where you started from, because once you have a degree 1, you really stop there. So the path argument, the Eulerian path argument, is kind of similar. It's going to be more general than just degree 1. This is a very pretty basic one to see, but we can generalize this a bit more. But it's going to kind of be a similar argument. There's this idea of going to a vertex and going away from a vertex, and it will depend on the degree it will turn out, if an Eulerian path exists. So that's where we'll start next time. We'll solve the bridge of Königsberg problem. But hopefully this was a good introduction. Got some definitions out of the way. And next time we can really start to talk about some more interesting ideas. But I hope you enjoyed a little introduction to graph theory, and hope you'll keep watching and keep loving graph theory. All right, thanks for watching, and see you next time.